In this video, we'll be looking at rational functions of the form ax plus b over cx plus d. Our previous examples have all involved rational functions where the denominator is some polynomial, either so far linear or quadratic, and our denominator is a constant. And now we're introducing a case where our rational function has a denominator that is also a polynomial, in this case a linear polynomial. So we're going to start by determining the key features of the function f of x equals x over x minus 2, and we're going to see what the graph of the function looks like. So looking at f of x equals x over x minus 2, let's start listing our key features. Let's look at the asymptotes. First we'll deal with the denominator. X minus 2 can't equal 0, which means that x cannot equal 2, which gives a vertical asymptote at x equals 2. For our horizontal asymptote, we're used to seeing a horizontal asymptote of 0, so right on the x-axis, but perhaps having a linear function divided by a linear function changes that. So horizontal asymptotes happen at the extremes of our function. So they happen as x approaches plus or minus infinity. So we can sub in infinity into our variable x, and we'd end up with infinity over infinity minus 2. Any really big number minus a small number is just that number. So we get infinity divided by infinity, and we don't know what that means. It's a big old question mark. So we can't really figure out the horizontal asymptote this way. We could divide each term by x, which would give us a really complicated function to begin with. But all these terms, x over x, just simplify to 1. So our new function, 1 over 1 minus 2 over x, would just become, as we sub in infinity, 1 over 1 minus 2 divided by infinity. And now this changes things. As any number gets divided by a bigger number, it gets closer to 0. So we've kind of shown that when x gets bigger and it gets closer to infinity, our function gets closer to 1. So as the numbers get bigger, our function gets closer to 1, and the same would be true if we subbed in negative infinity. So we get closer and closer and closer to 1. So that tells us that there is a horizontal asymptote at y equals 1. So we have a vertical asymptote, a horizontal asymptote. Let's find the intercepts. So first we'll find the x-intercept. That happens when y equals 0. So the function would equal x over x minus 2. Here we cross multiply, which gets rid of the denominator. And now we have a different situation than we saw with our reciprocal of linear functions. We have 0 equals a variable. Different than when we would get 0 equals a number, which is not true. So this is telling us that there is an x-intercept at x equals 0. Let's find the y-intercepts. Y-intercepts happen when x equals 0. So finding f evaluated at 0, I get 0 over 0 minus 2, or 0 divided by negative 2. 0 divided by anything is just 0. So we get that y-intercept at y equals 0. So is this not enough information now for me to graph the function? I know I have a vertical intercept at x equals 2. I have a horizontal asymptote at y equals 1. And my x and y intercept at the origin, which I'll mark in red. So as I trace this curve, I know that the asymptotes kind of pull the curve closer and closer and closer to the asymptote. And it has to pass through that intercept at 0, 0. And now I could test some values on the right-hand side of x equals 2 to see if my function is going to be above the horizontal asymptote or below it. But these functions are all kind of reflections of each other in a way. So I think my second branch of the function would look something like that. And we can verify this in Desmos. If I go to Desmos and I graph my function x divided by x minus 2. There's a visual of what my function looks like, and let's throw in those asymptotes. There's the asymptote at x equals 2. Change that to a dotted line. There's an asymptote at y equals 1. Change that to a dotted line. So look again how the asymptotes pull the curve towards them. And just for verification, we can see that there's our x and y intercept at the origin at 0, 0. Let's try another one. Let's see if we can quickly sketch g of x and h of x and see how these graphs compare. So starting with g of x, I should be, and you should be, able to quickly identify your vertical asymptote, which would be at x equals negative 1/2. For h of x, our vertical asymptote would be at x equals negative 2, and I'm finding that by just rearranging the denominator as I set the denominator equals 0. The horizontal asymptotes, with my previous example I did some fancy dividing by x. We don't need to do that every time. The horizontal asymptote, if I think about the general form of these functions, which is ax plus b over cx plus d, the horizontal asymptotes are going to be at the value a divided by c. So my horizontal asymptote for g of x is going to be at y equals 1/2. And for h of x, it will be at y equals 3. My x-intercept happens when the function equals 0. So if I make the function equal 0, my denominator disappears, and now I've made my numerator equal to 0, and I can rearrange and just solve for x. So with the denominator equal to 0, g of x just becomes 0 equals x minus 5. So my x-intercepts happen when x equals 5 and y equals 0, or the point 5 and 0. It's a little bit more complicated for h of x. I'm looking at 0 equals 3x minus 4, or 4 equals 3x, or 4/3 equals x. So my x-intercept for h of x is at x equals 4/3, or the point 4/3 and 0. And then lastly, our y-intercept happens when x equals 0. If I make x 0, in g of x, I'm going to have negative 5 over 1. My y-intercept would be at negative 5. And for my function h of x, If I make x equals 0, my two x terms disappear, and I get negative 4 over 2, or a y-intercept at negative 2. So that's the point 0 and negative 2, and for my other functions, 0 and negative 5. Graphing now, I have a vertical asymptote at x equals 1/2, a horizontal asymptote at y equals 1/2, an x-intercept at x equals 5, way over here, y-intercept at y equals negative 5, way down here. So these 2 points have to connect, and we've got that curve type reciprocal shape, something like that. And since these are usually reflections of each other, my other branch is going to be up in quadrant 2 somewhere. So if you were sketching, I'd expect to graph something like this. My second function, which I'll graph in green, has a vertical asymptote at x equals 2. A horizontal asymptote at y equals 3. An x-intercept of 4/3 and 0. So an x-intercept of 4/3 would be just slightly over 1 on the x-axis, and a y-intercept of negative 2. Again, my shape probably is going to look something like this. Probably can do a better curve than that, but we'll show this in Desmos in a second. So here's our 2 functions. Let's look in Desmos and compare. So here's the first function, x minus 5 over 2x plus 1. We can see there's the x-intercept at 5, y-intercept at negative 5, and our asymptotes. Let me just link those out and turn on our second function, 3x minus 4 over x plus 2. Again, there's our x and y intercepts. Asymptotes all agree with what the work we did. Let's just end by talking about some shortcuts you can use when graphing f of x equals ax plus b over cx plus d. When you have a function in this form, the vertical asymptote is always going to be negative d over c. Always. The horizontal asymptote is always going to be the a value divided by the c value. This is because for the vertical asymptote, we're taking the denominator, setting it equal to 0, and rearranging. So no matter what, we get negative d over c. For the horizontal asymptote, we get a over c because we divide everything by x, which just leaves us with a over c when we make x very, very large, which gives us that horizontal asymptote. X-intercepts happen when the function is equal to 0 and y is equal to 0, which means that our x-intercept is always going to be negative b over a. And then finally our y-intercept happens when we make x equal to 0, which gets rid of the ax and the cx, which gives us a y-intercept of b over d. So you can use these shortcuts to plot functions of this form quickly. Okay, you don't need to do a lot of work once you've got the pattern down. And so we're going to practice how we can use these later on to graph quickly.